Okay, let's start this second day of the workshop with Leo from MIT, who will tell us about progress and results in the theory.
Great, thank you very much. Well, yeah, I'd like to, as many of the other speakers have already said, I'd like to thank Jonathan and Miriam and all the other local folks who are working very hard to make this into a really nice conference, working smoothly as far as we can all tell, even if there are complications behind the scenes. And for continuing this worthy conference series, which I think is excellent. I've been enjoying it so far. So today I'm going to talk about some progress and puzzles in the 4D F-theory landscape. This is work with some of these collaborators, Patrick Jefferson, Mankey Kim, Kobe Lee, Andrew Turner. These four are all here. And actually, I'm going to focus in particular on some recent work with my former student, Yinan Wang, who's now a faculty member at Peking University, and his student, Yihong Yu. But it'll also touch on some work with all these other fine folks. So the motivating questions for what I want to talk about today are, what can we say about the general shape of the string landscape? We've come a long way over the last few decades, and we have lots of different ways of describing string theory. What can we say about the shape in particular of the set of 4D vacua that this theory might give us? And similar to, but not the same as the swampland type of questions, there are of course questions about what is allowed and not allowed, but there's also a question of what is typical. And of course, this is a hard question because we need to do something about the cosmological measure. But at the same time, even using a simple counting measure and seeing that certain things are exponentially favored over certain other things can give you a sense of what might be typical and what might not be typical. And in that context, of course, one of the main goals is to understand how the standard model fits into that. In other words, are there many ways of getting the standard model? Are some of them more typical than others? If so, do the ones which are more typical give us useful predictions for observable physics? So what I want to do today is part of a general program of trying to address these questions in the context of the 4D F-theory landscape. So F-theory, I think, is unique in a number of ways in terms of the different approaches we have to string theory. For one thing, it's non-perturbative. For another thing, it gives us a larger class of vacua than we really know of from any other point of view. In principle, many of them come from heterotic, but involve extraordinarily singular situations with small instantons, which are not really as well analytically under control. And this is also a connected set of vacua. Even though in 4D, once we get a superpotential, the vacua themselves are discrete points, they live in a larger connected space of elliptic Calabi-Yau fourfolds, which is really essentially one big connected space with a superpotential on it. So it really gives us an unprecedented scenario in which to try to understand the global structure of the landscape. And furthermore, when we look at F-theory, we see that there are many common features between F-theory with 8 supercharges, as in 6-dimensional n=1 compactifications, and theories with 4 supercharges, that is 4D compactifications. So an example of that is the appearance of these ubiquitous rigid or geometrically non-Higgsable gauge group factors that arise in almost all the vacua, which gives us some sense of what a typical vacuum might include. So the kinds of questions I want to ask today, specifically in this context, are what is the relative abundance of the different rigid gauge groups in which the standard model might live? So in particular, focusing on E6, E7, and E8. And a more technical question, which I'll mention later, is what is the abundance of the remainder cohomology, which I won't get to too much today, but I just want to bring that up as the kind of question that we're interested in looking at. Okay, so what does the 4D F-theory landscape look like? So this is actually a pretty good picture of the shape of the 4D F-theory landscape. This is a picture from 25 years ago of a bunch of Calabi-Yau fourfolds. This actually turns out to be fairly representative of the shape of the landscape, the set of allowed Hodge numbers for those elliptic fourfolds. And although these are just general Calabi-Yau fourfolds, it turns out that virtually all of the Calabi-Yau fourfolds that are known, and in particular, virtually all of the hypersurface Calabi-Yaus are elliptic. And this is has been studied extensively by Laura James and the Virginia Tech group, and by myself and former student Yuqian Huang, finding that just a huge, overwhelming fraction of the known Calabi-Yaus are elliptic. So this is really a picture of the set of elliptic Calabi-Yau fourfolds. So in this space, there are some special favored points. So one example is this point up here, found early on by Kandelis, Prevalov, Rajesh, and the other folks that studied these things. But more recently, we studied it with Yinan Wang in the context of the elliptic fibration over a certain base, B max H31, which appears to have the most different possible flux vacua of any of the F-theory geometries. So this geometry here is an elliptically fibered Calabi-Yau fourfold. It gives rise to an F-theory gauge group of E8 to the 9th and a bunch of F4, G2, and SU2 factors. These factors are highly typical for F-theory vacua, as we will see further. And it's got this huge number of flux vacua. Oops. A second base of interest is at the other end of this 45-degree shield. This was studied recently by Yinan and also earlier found, of course, by Kandelis, Prevalov, and Rajesh. This is the elliptic Calabi-Yau fourfold with the largest known H11, and it has an enormous gauge group with thousands of factors of E8 and SU2 and G2 and F4. And it is characterized by having, the largest number of flop phases. So if we think about just distinct geometries, if we don't worry about how many possible fluxes you could put on a geometry, in some sense, this base contains the overwhelming plurality of all of the geometries in the 4D F-theory landscape, just by virtue of its various flop phases. Now, what I want to look at today is a more typical base, which would live down here in this lower left-hand corner. That is, if we think about the set of possible F-theory bases, there are many of them. And part of the goal of today's talk is to discuss how many of them there are and look at that space. But the ones I'll be looking at lie in what I would call the bulk of the space of bases, which is somewhere down here. So what is the right measure to use when looking at this vast proliferation of vacua? This is, of course, an unsolved problem. The standard story of flux vacua, Ashok, F. Douglas, et cetera, says that you just count the number of different flux vacua, and that would indicate that this geometry that I had in the upper left corner, max H31, dominates. If we look at just geometries, then we might think that counting geometries would suggest that max H11 dominates. And if those approaches are correct in terms of how we should think about the measure, that suggests that if the supersymmetric 4D F-theory landscape is any kind of guide as to what we should see in our world or physics coming from even non-supersymmetric vacua of string theory, then the most likely place to find the standard model would be in a rigid E8 factor. But it's actually quite tricky to get the standard model out of a rigid E8 factor. Tian and Wang have looked at that a bit. I'll talk a little bit more about that later. So for that reason and a number of other reasons, what I want to consider in this talk is the broader set of allowed threefold bases. I'm going to start today with toric bases, and this is the recent work with Wang and Yu that I'll focus on today. And then I'll say some brief things about going on to non-toric bases, which is an ongoing project with Menke and Kobe, who are here. So the motivations here are to get a better global picture of the full landscape, to investigate the prevalence of these different kinds of gauge factors. In particular, I'm interested in understanding the prevalence of E6 and E7. Last summer at the String Pheno conference, I talked about some recent work with Kobe, who's here today, in which we used flux breaking to break rigid E6 and E7 factors down to the standard model, and very naturally get 3-generation models with a wide class of vacua that may or may not be typical. So part of the question here is, how typical are these E6 and E7 factors? We didn't see E6 and E7 factors at the tips of that landscape, but do we find them in the bulk? Again, we really don't know the right cosmological measure. If, for example, there is a finite number of vacua, even if very large populated, then we would get a very different sense of statistics than if there's a truly infinite landscape. Things that are way out in the corners may, in many models of cosmology, be harder to reach. Of course, the standard story in kernel inflation is that there's an infinite number of samplings of everything. But in the spirit of Thomas's talk yesterday, maybe there's a sense in which even the existent multiverse is in some sense tame or finite, in which case it would actually push us down into the bulk of the set of vacua. So anyway, for whatever reasons, what I want to do today is get a little better picture of the set of bases that support elliptic Calabi-Yau threefolds. Before I get into that, let me just recall the 6D story where there's a very similar landscape. So here's the set of toric hypersurface constructions of Calabi-Yau threefolds. There's about 400 million of them. And in this work I mentioned with Yu-Chen, we showed that all but about 20,000, just a tiny little sliver over here, all but that sliver emit an elliptic fibration. So this is really a picture of the set of known elliptically fibered Calabi-Yau threefolds. All of these are elliptically fibered over a toric base. And in some work a while back with Dave Morrison, we explicitly constructed all 61,000 toric bases that are acceptable for a 6D F-theory construction. And then this was extended in work with Gabriele Martini to all semi-toric, i.e. having a single C-star action bases. And then with Yinan, we developed an algorithm for constructing all non-toric bases, which starts from large H21, gets kind of bogged down around here because of some computational and difficult math problems having to do with infinite numbers of generators of the Morricone and that sort of thing. But we constructed, we believe, all possible non-toric bases giving H21 above that line. And there were only a couple thousand of them. So the upshot of that story is that toric bases are a good representative sample, certainly at large Hodge numbers. And as far as we know in 6D physics, there's nothing really special that non-toric bases have to offer. They should give you a similar shape, a bunch more stuff in the bulk, but nothing particularly special. 4D is a bit different. So let's talk about, now come back. This is sort of an object lesson for what we want to try to do in 4D. We want to try to construct first all the toric bases and then all the non-toric bases, and then really have a global picture of this landscape. So what happens when we try to classify the bases for elliptic Calabi-Yau fourfolds? So for a twofold base, the geometry of a base for a toric two-dimensional fan, there's only a unique triangulation. That is, there are not different flop phases on the base because there's a unique triangulation. If you don't know toric geometry, that's just a simple fact about the fact that if you draw a bunch of points on the plane, there's a unique way of drawing a sequence of rays that covers all of them. In 3D, there's an additional piece of information, which is the triangulation or flop phase of the base. Now, in some previous work that Jim and Cody Long and the Northeastern group and that we with Yinan did on studying this class of threefold bases, we consider different flop phases or different triangulations as geometrically distinct. And this gave various lower bounds on the number of geometries in the range of 10 to the thousands. And then, of course, I mentioned that one base that seems to have 10 to the 44,000 triangulations. So there's a very large number of geometries, again, dominated if we take triangulations as distinct by that thing in the bottom right corner. What I want to do today is to consider different triangulations of the same 3D base as equivalent. That is, we're just going to consider the polytope data. And there are a number of reasons for doing this. First of all, it simplifies in some abstract sense, at least the statement of the problem, in that now we're trying to classify polytopes and not entire toric fans. The other more subtle reason for this is that actually much of the physics doesn't depend on which flop phase you're in. If you have some complicated threefold base and you do a flop, it does not change the rigid gauge group. And it might be something that's actually quite hard to see in the low energy physics. There's some kind of transition going on, but it's a pretty mild transition. This is related to some recent work with Patrick Jefferson and Andrew Turner looking at 4D constructions with chiral matter, where we found that the form of the intersection form on the vertical 2-2 cohomology is resolution independent. So there's a sense in which some important geometric structures that govern the physics of Calabi-Yau fourfolds are, that is an independence of resolutions, but that also is related to an independence of flop phases. And some ongoing work with Patrick and Mankey, we're exploring the independence of the physics of these kinds of things of more general classes of flops. So in other words, there are multiple reasons why this is maybe a useful thing to think about. Another way to say it is this just gives us an easier way of categorizing the landscape, and we can, after that, worry about triangulations if we wish. So the math problem that we want to solve is we want to identify all integer 3D polytopes, delta, so that the dual, this is really the 6 times the polar dual, or in the F-theory language, this is the G polytope. This is the thing which carries the monomials of the G in the Weierstrass model. So basically, this is just the condition that we have a good F-theory model. So there's a finite set of polytopes that satisfy this boundedness condition. This is a very easy statement, a very easy math statement to write down. It's a little trickier, at least as far as we've been able to get, to actually do this computation. One comment is that these polytopes will include simple orbifold mild singularities in the bases, which are pretty mild from the point of view of F-theory. So we're going to include those. Okay, so the particular project here is to try to identify and give a statistical picture of the set of base polytopes. So these are 3D polytopes that characterize potential bases for 4D F-theory models. And in principle, if we can characterize these, this will give us a complete picture of at least the toric part of the 4D F-theory landscape, analogous to what we've got in 6D. So this is somewhat of a computationally challenging problem. There are far too many of these polytopes to just make a list. I'll talk a little bit about the numbers. So I and Yinan and his student have got a bunch of codes running on clusters. So we've got hundreds of nodes working on doing various statistical estimates to get the shape of the landscape. And I'm not going to get way into the technical details. I just want to give you a little flavor of what we're doing and where we are so far. This is a work in progress, so I'm not 100% sure of a few of the things I'll say, but it'll be interesting to tell you about them anyway. One important point to make here is that each polytope has an infinite number of realizations through SL3Z transformations, right? You could have an arbitrary SL3Z rearrangement. And so we have to mod out by that infinite degeneracy in doing a complete scan. Otherwise, the answer is there are an infinite number of polytopes, right? So there are an infinite number of polytopes satisfying this. We need to identify them up to equivalence under SL3Z and make sure that we keep only one representative of each. Okay, so we're using 3 approaches to do this. The first one is we take a box of a fixed size, we pick a bunch of points, look at the convex hull, and see what we've got. That's a polytope. Then we can use that for a partial estimate on various statistics. This turns out to be good when the number of vertices of the polytope is relatively small. It's computationally not so good when you get more. A second approach is to do a kind of a Monte Carlo. This is related to a method that Yinan and I used years back in the work I mentioned where we were using triangulations as being different. The idea is the set of these polytopes can be thought of as a graded graph where the grading is the H11, and the graph basically has an edge connecting any 2 polytopes which differ by 1 in H11. So basically, you just can move up or down by adding or subtracting a vertex. So the idea is you take something like P3, you add or subtract 1 vertex at a time randomly, put it in the canonical form and repeat. There are a couple subtleties here. One is that you need some cutoff for the distance to add a vertex, because there's no simple way of knowing how far you have to go if you have a very squashed polytope to add a new vertex. And the second thing is that if we do this Monte Carlo, there's a very large number of these bases, and it's not quite clear whether we have globally thermalized, and I'll talk more about that. A third approach is to construct all of the minimal dual Nabla-6 polytopes and then sample in fixed corresponding boxes, which avoids the problem of having to check the Nabla-6. And in some sense, this is maybe the most robust way of doing it, but it's a little complicated, and we're working on that one. The first 2 we've implemented, so I'm going to tell you some of the results of the first 2. We have cross checks, and we should be able to correlate it all with approach 3. So hopefully, with all 3 approaches, we should have a pretty robust way of saying that we actually know what we're talking about, even though the numbers are very large. Okay, so here's what comes out of the Monte Carlo so far. So one of the tricky things is that this Monte Carlo is a bit slow because parts of that step scale polynomially in H11, maybe as the 3rd or 4th power. So once you get up to H11 is 400, each step takes like 400 cubed steps, so it's a little slow. And the cluster has found nice results up to about 400. I mean, of course, things start to equilibrate apparently around 400, and there's various tricks you can use to explore beyond that by putting a weighting in the random walk. I won't get into that, but and we've got some runs going on. I was hoping to have a few data points over here, but they're not quite in yet. But what we see right now is that, first of all, you can verify that the results are independent of the cutoff I mentioned. The peak seems to be around H11 is 430. The number of polytopes at that size is around 10 to the 41. So a big number, too many to list on the computer, but nowhere near as big as 10 to the 40,000 or 10 to the 200,000. The number of vertices is typically around 45. The total number of bases based on this looks like it's around 10 to the 43. The one caveat here is that while these are thermalizing, there may be some narrow little path that could lead you onto some bigger set, and we'd like to rule that out. We're working on ruling that out. It's possible that is hidden in some very skewed polytopes. So there's a little technical issue there, which makes me label this as a tentative conclusion. Okay, but on the face of it, this seems to be the picture of what's going on. We can look at the typical gauge group factors. As we approach this peak, this is a typical gauge group for a typical base. Lots of SU2 and G2 factors. By the way, that's a typo. That should be SO7. If you look at the graph, there's, you know, these are the various rigid gauge groups that can be forced on you. Lots of SU2s, lots of G2s, lots of F4s, some SO7s. And at this scale, we have typically order 1 E6, order 6 E7s, and order 10 E10s. So actually here we see on the order of as many E7s as E10s, which I think is interesting. That gives us plenty of room in this typical base for constructing a standard model from either an E7 or an E8 with lots of other stuff around, which of course has a natural interpretation as dark matter. So if our universe comes from something like a typical base like this, we might be living in the E7, E8 factor in one of those, and then the rest of this might be some kind of dark matter. One comment is that these factors that you saw in the really big bases, the SU2, G2, F4, and E8, these grow roughly linearly in H11. And those come from the fact that, that if you go to a large base, you have these faces at distance 6 from the origin, where those things are basically all the ones that dominate. Michaela, you had a question? I would say, okay, so the question is the measure. If you're measuring by fluxes, then the generic gauge group should be that one with E8 to the 9th. If you're measuring by geometries, it should be the one on the far right. But if you're measuring with respect to bases independent of flop phase, then I would say this should be the typical base. So depending on how cosmology works and how the distribution works, this is one possible answer to the question of what is a typical gauge group. I'm not sure I could argue for why this would be typical rather than the maximum flux one, but it's a possible answer for a typical gauge group. And it seems plausible that this is not in contradiction with observed physics, right? If that's the typical gauge group, we can see how the standard model in dark matter fits naturally into that. Now, with broken supersymmetry, all kinds of things that may be different. But again, the goal here is this is as close as we've ever come, I think, to having a real picture of the global structure of the landscape. So we're going to do our best to figure out what's typical. And this looks pretty typical to me by the counting measure on bases without respect to flop phases. It could. That's right. There's different stories in which it might do that. Yeah, thanks, Jim. Yeah.
You argue that the starboard come out of one of the 7 or 8. Is it also possible to argue that the starboard comes right away from the 231?
It is very tricky. So this is something that Jim and I and Antonella and Julia Shainson investigated. The tricky part is getting the U1 in that case. So if it wasn't for the U1, I would say absolutely, it could be an SU3 cross SU2. You would also need a rigid U1, and these typically do not have rigid U1s. There's some nice work of Yinon characterizing precisely what you need for a rigid U1. We found some rigid U1s in the work with Gabriella Martini for non-toric bases. You need a non-toric base, first of all, so none of these have a rigid U1. No, because it wouldn't have the right interaction with the SU2 and SU3. Let's talk about that more. There might be some interesting story there, but it seems harder. We should talk more. Good, because I'll mention this in a little bit, but the tuned gauge groups, first of all, you have to do a lot of tuning, so they're rare in that sense. But in particular, these things are so chock full of gauge groups that there's very little room to tune anything. So I'll refer back to this at the end of the talk, the rigid versus tuned. So let me actually refer back to that in 3 minutes. Well, the problem is, once you have so many gauge groups there, it's very hard to find a divisor that you can tune an additional gauge group on. That's the issue. It's for the really big ones, there's no space at all. And it's an interesting question, actually, whether in a typical base like this, there exists a divisor on which you could tune one of the, so I'll come back to that in, I think, 3 minutes. Okay. Just quickly, I mentioned this other approach of looking at points in a box, and here we have 10 vertices in a box of size 19 cubed, gives this distribution on H11, this distribution on gauge groups, and in particular, we have a cross check which shows that at one point we checked that this gives the same prediction as the Monte Carlo, so that cross check assures us that we seem to be doing the right thing. So some comments here are that the typical base seems to have around H11 is 400, H11 of the corresponding fourfold is 1,000. We certainly seem to have E7 factors on a typical base. And the question here is, what does typical mean? We need to understand thermalization a little better, and the number of bases looks like about 10 to the 43. So let me say 2 words about going beyond toric. So we could try to consider now bases that are a hypersurface in a toric fourfold, or a complete intersection even further. And this is, again, work with Menke and Kobe that we're doing some stuff on. For any given toric A, there is a finite number of bases that you can construct by hypersurfaces because of the constraints on the anti-canonical class. And you can compute the structure of the base using those methods. The tricky thing is, there are an infinite number of toric fourfolds A in which you might consider hypersurfaces, and you will get an infinite number of copies of certain bases. So for instance, if you take a P1 bundle over B and give it an arbitrary twist, that's an infinite family of threefold bases, and they all admit a B hypersurface, but that's not very interesting. But it's a bit tricky to find a way of giving a finite classification of a set, which matches with the fact that we know from Dicerbo and Svaldi that there should be a finite number even of non-toric bases B. So there's some technical issues there. We have some ideas. I'm not going to talk more about that, but the motivation here is, so why do we care about this? I said that for threefolds, non-toric doesn't really give us much extra. The big difference in fourfolds is that there's this decomposition of middle cohomology into the vertical part from the intersection of divisors, the horizontal part from variation of H31, variation of the complex structure. And then there's this remainder part, which was studied by these folks. And it turns out that that remainder cohomology is needed for hypercharge breaking. This was found back in the Beasley, Heckman, Vafa, Donagi, Weinhold, and many others here studied the SU5 breaking using this hypercharge, which needs to live in a REM cycle and therefore requires a non-toric base. With Kobe, we've also been studying these E6, E7, and to get a good or fairly realistic construction with a flux breaking of E6 to E7, you need to first break to SU5 and then use the same kind of hypercharged flux breaking. So to get the apparently realistic models of the standard model, you need this REM cycle. And so there's a question, are these REM cycles typical? Brown and Watari speculated that they are, but we would like to have a more quantitative assessment of the generality of that and understand in particular if these REM cycles are typical, what is their shape? What is the typical divisor on which the standard model gauge group might live? So let me conclude essentially with a sort of overview of the different standard model type constructions in F-theory. And this comes to your question, Miriam. There are lots of nice constructions of standard models, either using a tuned SU5, there are no rigid SU5s, or directly tuning the standard model using something like this F11 fiber that Clebers, Mayorga-Pena, Ullmann, Paragua, and Reuter constructed, and Miriam and Ling and Jim and many of the others here in the Penn group have been extensively studying quadrillions of these standard model constructions. With Patrick and Andrew and Nikhil, we've been studying a broad class of Weierstrass models that includes the F11 models, but is some other large class of tuned standard model constructions. So this is certainly a possibility. These seem to be very rare in the landscape for 2 reasons. One is that you have to tune a lot of complex structure moduli, which ostensibly requires either tuning of moduli or picking of fluxes that forces you to that particular locus. The more serious problem, as I alluded to a moment ago in response to Miriam's question, is that In the large bases, it's very hard to find divisors which are sufficiently far away from the rigid gauge groups that you can tune something there. In particular, if any divisor intersects a divisor with like an E8 on it, you're not going to be able to tune the standard model on it, because if you tune the standard model on it, there would be an E8 gauge group with 4-6 points and bad and superconformal matter, and actually that would break the theory if you had SU3 hitting an E8. So that's my biggest concern there. Now that we're getting a better handle on what a typical threefold base is, it's not as big as the ones at the very end. So it's actually possible that there are divisors there where you could tune the gauge group. And actually, that's a great question for further study. So let me not dismiss that possibility so readily, because with this more typical base, it's smaller. There might be room for a bunch of divisors where you could do that. And that's a good question for further study. I didn't list that on my questions, but I think that's a great question for further study. Take a typical base here and ask that. There are a lot of E8 factors, but it's actually very tricky to see how to get an E8 to work. The problem is, first of all, that E8s tend to have superconformal matter. And in the work of Tian and Wang, they tried to use that to construct standard model matter. This is a very murky business, what happens at these 4-6 points on the E8 locus. I'll come back to that in just a few minutes. With COBE, we tried to look at flux breaking from E8, and you don't get chiral matter of the kind you like in the same way that you do for E7 on E8. So it's just harder for various reasons. It's not necessarily impossible, but we don't know how to do it. The E6 and E7 factors are rarer, but they seem to be common on typical bases. And as I say, we do have this flux breaking story, so that may be the most typical route. It may not be. I mean, there's a lot of things one has to understand. So let me just close with a list of puzzles and open questions. I mean, part of the reason I wanted to give this talk is I have more questions than answers here. I think this is a very exciting time that we have such a big picture of the landscape of 4D n=1 supergravity theories, and we can try to ask sensible questions about what the entire landscape looks like. So here are some of the questions related to what I talked about that I think are interesting. Can we say enough about the measure to determine what's really typical? That's, of course, a really hard problem that cosmologists have been puzzling about forever. Is there something wrong with most expected flux vacua? So to really argue that the E6 or E7 factors are even relevant rather than the things at the very end, there either needs to be some statement about the measure that pushes you into the bulk, or there has to be something wrong with some of the flux vacua that appear by the naive Ashok Dennis Douglas story to dominate. Now, there's a discussion about whether those flux vacua really work out, and that might help with this story. Another question, which, as I say, we're investigating, but I think is quite interesting, is are the base flops essentially irrelevant in the sense that they're not changing much physics, and the measure really might not include those. As I say, we're investigating this. Does a typical threefold base give remainder cycles, which is key for these flux breaking stories? Can we make sense of strongly coupled matter? So this ties into some of the SEFT things, which lots of people talked about yesterday. Craig and Ibu and Monica and Michele and others have been talking a lot about superconformal field theories, particularly in 4 dimensions. And understanding those superconformal field theories is critical to understanding the strongly coupled matter that appears, for example, in the E8s and in other contexts, which we might need to really get a good understanding of phenomenological physics. And so really the bottom line question is, what is the most typical standard model construction? And once we figure out what is the most typical construction, what does that imply for further physics? And I'll stop there.
Thank you. Beautiful talk, and also a very impressive landscape for these common happens that there is one big difference between theories 4D and 4D = 1.
Yes.
4D = 1 have almost always been dimension.
Yep.
Like we argue that essentially all of them, which don't have a series for extension of corner,
Yep.
you would get this potential.
Absolutely.
So the question of what is typical cannot be, I think, decoupled from that answer to the question of what is potential, because potential will try to be away from something like typical.
Yep.
And in particular, the rigid ones are a good place for the potential, because the rigid cycle is nice for the gases contribution.
Yeah.
Therefore, we're trying to read out. So I really think that part of this question is maybe I'll add one line there from the top maybe figure out effective ways to deal with supertension and what does that mean? I think that's a crucial question.
Yes, I 100% agree with you. In some sense, I view this as one part of a multi-pronged process. And in order to really understand what's typical, I would say first we have to understand what's a typical base, because everything is built on the base. So over each of the points, over each of these 10 to the 41 points, there's a Weierstrass model moduli space, which has an enormous number of different F-theory models, each of which has a different gauge group coming from different singularities. There's some stratification. To understand where you are on that, as you say, you need to understand the superpotential. To understand the superpotential, you also need to understand fluxes. So I kind of see it as first we need to understand the bases, then we need to understand the geometries on each base, then we need to understand when you put on the flux, what does that generate in terms of superpotential, and then what does that really generate in terms of typicality. So this is really a first step, but I think it's a necessary first step to even start to address the important question which you're asking. Yeah.
How do you make the comment?
Yeah.
It's driven by the beautiful pictures you showed for the mass people, 3 folds and 4 folds. Seems like, I mean, it's a naive statement, but it seems like a table should not be any folds. You should get a stable square and line anything from there where the lines end at the twice making the square. Is there any explanation on that, or at least a number that you have seen using on the thing, right?
Absolutely. That's a great speculation. I believe it is true. I have no idea how to prove it.
There's an angle to the stable structure.
Yeah, I mean, there is a sense in which you expect if you tilt this by 45 degrees, as people originally did it when they were doing mirror symmetry, it's sort of natural that the thing in the middle has the same height. Honestly, I don't have an explanation of that phenomenon. It's true in the example, but I don't. Which would mean that in that, yeah. And I think you're absolutely right that it looks like it gets squeezed, and it might be interesting to get enough of a sampling in higher dimensions to confirm that. We can talk offline. I think that's a fascinating speculation, and I'm sure it's true.
I like all the discussion about measures for this. Kind of related to that, I think for the first time now, maybe the group is ready to start answering what is typical flux rating. So these not typical clusters coming right now. So you can sort of countermeasure on fluxes. You have a statistic there that
Good. So that is something that we have started trying to ask. I mean, Mankey is an expert on some of these flux questions. So there's a project that Patrick and I and Mankey are working on, which involves getting the full intersection form on the H4 lattice using mirror symmetry and our understanding of the H22 vert, which I've actually talked about this a couple of times, and we haven't quite finished that project due to some technical issues. Once we have that answer, I think we will be able to start more meaningfully talk about a typical flux, because you need that intersection form to, in my mind at least, to make that next step. But yeah, and then there are questions about, what happens to the complex structure. It's a great question, and it's definitely on the agenda. It's on the radar, and I'd love to talk more about it, but we haven't gotten there yet. Yeah.